Hello, I'm Joe Charest from Draper's Biomedical Engineering Group, and I'm going to talk to you today about our innovations in organ assist technology. Organ failure is obviously a severe medical condition, but what's scarier is how common this condition is. Of the top 10 causes of death in the United States, 3 of them are directly linked to organ failure of the liver, lung, and kidney. If we look at just kidney failure alone, 1.2 million Americans have kidneys that are failing, 500,000 have kidneys that have effectively completely failed. And of those 500,000 with failed kidneys, despite our treatments, 20% of them die every year. So this is a very big problem. Some concrete examples. A premature infant born with underdeveloped lungs effectively cannot breathe. That's organ failure. An aging patient who has a failed liver. The liver can no longer process the toxins in the blood as it normally would. So what do all these people have in common? Their organs have failed, and their blood has to be drawn from them, processed in the way it normally would by organs, and then returned so that they can survive. So this requires an organ assist technology. But what's the problem with the current organ assist technologies? If we look at a lung assist device, for example, this is a premature infant hooked to a lung assist machine. The blood is drawn from this baby, oxygenated by the machine, and returned. This requires a very large volume of blood in a complex machine. And the machine sometimes is much larger than the total volume of blood in the actual baby. And so the blood has to be supplemented with blood from a blood bank. This adds cost, it adds complication. We can't treat as many patients as we would like to. The reason that volume of blood is so large is because the device is inefficient. As this large volume of blood is transitioned from the patient into the machine, it does not undergo a smooth transition from a large blood vessel into the small structures that oxygenate it. This lack of smooth transition can cause cells within the blood to be damaged. It can cause activation of different components within the blood that cause inflammation in the patient, and it can cause clotting. The way we treat kidney failure now is through a process called hemodialysis. Blood is drawn from the patient, run through a machine. The machine removes toxins and balances the solutes and water within the blood. So what's actually happening is you're taking 3 days of kidney function and compressing that into only 3 hours. So this results in massive swings in the blood chemistry of the patient, which causes all kinds of side effects. In addition, a very large volume of blood is required to do this in such a short amount of time. That blood flow is very, very high, and that actually taxes the patient's heart. If we look at nature and we look at actual organs in the human body, they are efficient, and they have very smooth transitions of blood. So our idea was to look at what makes those organs so efficient, copy those structures, and integrate that into an organ assist technology. So in the lung, we have these microscale complex structures that give you a very high surface-to-volume ratio. The transfer of oxygen into the blood is very efficient. If we look at the kidney, the basic functional unit is the nephron. Once again, a high surface-to-volume ratio structure. This gives you a lot of efficiency. And at the same time, it's compacting a wide variety of machinery into a small space because of the complexity of the process that's needed to be performed by the kidney. And finally, the human body uses its blood vessels to transition high volumes of blood into these small-scale structures. It branches those vessels in such a way that it goes from large to small in a very smooth way. So this results in no damage to the blood. So this is a logical approach. We're not the first to think of this. Why hasn't anyone done this before? The bottom line is making these complex structures at a microscale is very difficult. Unless, of course, you work somewhere where creating complex microscale structures happens on a daily basis. So at Draper, we've pioneered using microfabrication and microelectromechanical systems, fabrication techniques to create microscale structures that are very complex to be used in guidance systems and other resonant structures. So we zoomed in on the human lungs, and we looked at what's inside of them. And essentially, we have these branching structures that take the airflow to a very small conduit, and that gives you that high surface-to-volume ratio. So we were able to copy that and copy the branching within those structures. We integrated that into a device, and we can actually oxygenate blood just as well as you could with the normal oxygenators that you have today, except it's done with a much lower volume of blood, and the device is much smaller. If we look at the kidney and we look at the nephron again, the basic functional unit, we were able to copy the small-scale structures and give you the high surface-to-volume ratio that gives you the efficiency. But we also know that there are these different pieces of machinery within the nephron, and they have structures that run parallel to each other and loop back on each other. Those create concentration gradients, and that allows the kidney to be very selective in what kind of toxins it removes and what kind of water and solutes it reclaims and saves for the body. And we could copy those structures as well. And finally, we needed a way to transition the blood from the patient's blood vessels into these small-scale structures. And we did that by using a micromachining technique to create a mold that had features that were as large as some of the larger blood vessels, but also as small as these microscale structures that you have in the organs. So we could transition those very smoothly and create the exact flow pattern that we wanted. The human body has one last trick that makes the organs so efficient. It has living cells within all of those structures. So we took a similar approach, and we took cells derived from the human body, inserted them into our microscale devices, and grew those cells in a way and put them in an environment that makes them behave as they would in the organ. So this way they're operating in an optimal fashion, and they can perform those same functions that they would inside an actual organ. So this is fascinating science, and it seems like it's very far in the future. So the question is, when can we actually apply this so that we can help patients? And the answer is, we're actually doing this now. We've entered a product development partnership with a major medical device company, and we're in our third year of testing prototypes that use all these technologies to create an organ assist medical device. It's a technology that has the potential to treat over 500,000 US patients, and that will go a lot further as we develop new applications for this. The bottom line is, we're on track to take this technology and transition it into the hands of clinicians within a few short years.